Welcome back from that ad break. I hope you've had a bit of something to relax and think about, the questions we've been asking. Remember, the one question we said right at the beginning is how can we change the magnetic field pattern? And hopefully you've got some ideas already. And to put it more formally, we can say, how can we change the magnetic flux? Well, here are some things to consider as we're looking at changing the magnetic flux. We could say that we could increase the current. And you've seen that the pattern changes, and if the pattern changes, that means the field lines would be better. Would be closer together. We'd also could increase the thickness of the conductor. We put, in other words, reduce the resistance. If we had a thicker conductor, we'd have a stronger current, and we could also change the shape of the conductor. Remember, we could change the magnetic flux in terms of its direction by changing the direction of the current. Let's investigate this idea of changing the shape. And the first shape we're going to do is simply to say, let's bend the piece of wire. Instead of being a straight piece of wire, let's bend it into a loop. And so here's a picture of a simulation where we're going to investigate the magnetic field around this looped wire. Now remember, we've got in this position over here the positive, here's the negative, so we know that the current is coming around the loop in the direction that I've indicated in those blue arrows. Just to make absolutely sure, before we go and look at the simulation, let's check out the right-hand rule to make sure that we've got it right and to see that these compass needles are pointing in the right direction. So we point the direction of the current is up like that, then you'll turn the fingers, and as you can see, I hope you can see, that these little compass needles are pointing in an anti-clockwise direction, just as we would predict. Whereas if I go to this side and I say now the current is coming down, then the needles are pointing in the other direction, it's going clockwise. So that's quite an interesting observation in terms of applying the right-hand rule and seeing what the effect is. But you know what? Let's go and investigate. So here we have the application, and there are a couple of things that we can do. We can, first of all, recognize what happens if we change the direction of the current. Now, look, the needles all changed. They're now pointing in the opposite direction. And if we were to look at what's happening to the right-hand rule here, you'd see that we can actually move this right hand along here, and in that position, you can see that the current is going upwards, and the circular green lines are showing you the same direction as the red compass needles. If we move it around, this magnetic field is all around the loop. It's not just in one position. It's everywhere along where that wire is. But we're just showing that the different direction is where the lines are separated by going through this cardboard surface. Now, I'm going to take that off. I'm going to say, let's adjust the position of the wires. So what do you think will happen to the compass needles if we move the wires closer together or further apart? Well, let's try it. So if we move them further apart, you'll see the loop's got a whole lot bigger. And in the middle here, some of these compass needles are starting to align, but some of them aren't quite as aligned. If we bring them closer together, you'll see that there's a stronger field in the middle here. More of those compass needles are kind of pointing in the same direction. It's not as clear as I would have liked it to be, but anyway, that's a little bit of an investigation. So now that we've looked at that, let's take a different view of it, and let's just slow down and have a look at how we represent this magnetic field around a loop or bent piece of wire. So I'm going to take different viewpoints. And the first viewpoint I'm going to have, I hope you can see, is just a half coil. It's a half loop. And we're saying that from the positive end where at this point it's positive, and we recognize that the current is going from the positive to the negative as indicated by both the blue arrow and the white arrow. And so we've got the direction of the current. But what do you think the direction of the magnetic field is going to be? And how do you think we could find it? Well, the answer is easy. You're going to use your right-hand rule. You're going to say, let the thumb point in the direction of the current. Curl of the fingers is going to give you the direction of the magnetic field. Now, I've done a little bit of preparation for this because I didn't want to be drawing too much. And what you can see is that on the outside of this loop, the field lines are coming out towards you. So they're coming towards you. The fingers are pointing towards you. But if I use the right-hand rule over here, for example, you can see that they're going into the board. And over here, they're going into the board. And if I do it on this side, where the current is going down, it's going into the board. And that's why I've put all these crosses on the inside. Now, notice the difference in the field inside the loop and outside the loop. Outside the loop, the field lines are non-uniform. They're quite spaced out. They're separated. They're just like we had with the straight piece of wire. Those that are the field close to the piece of wire, quite strong. Far away, weaker and weaker. But on the inside, there's an overlap between the ones that are far away from this end and the ones that are far away from that end, and they've kind of clustered together. And so what do you think we can say about the magnetic flux? Well, let's have a look. And I hope you can see that I've drawn the same red square. And if you look carefully, you'll see that there are lots of field lines inside that area. So this is an area of high magnetic flux. Whereas if we go to this point, you'll see that here it's low. Over here it's high. So this tells us that this is a strong region of the field, and this is a weaker region of the field. And that's quite important. Where it's strong, all the field lines are pointing in the same direction and they're tightly packed together. It's a more uniform field. And it doesn't matter where you are within that, you'll feel the same, experience the same sense of the magnetic field. Whereas outside the loop, on the outside, it's weak and it's not going to have as much of an effect. Now, I wonder where we've seen something similar to this. Can you think about where you've seen field lines clustered together and they're quite dense, and where you can see them spread out? Well, maybe this will jog your memory. If we go and have a look at our bar magnet, what you'll recognize around the pole, the North Pole, looking your eye over here, the field lines are all coming out. That's why we've got those ones. And over here, if we look over here with the eye, we'll see the field lines are all going in and they're clustered together. That tells us this is strong. And where they're strong, in terms of the magnet, we say that's a pole. If we add to the field lines on the outside, you'll see they are spread out. And that's exactly what's happening here. So what I'm trying to illustrate for you is what we saw earlier around a coil is very similar to what we see around a magnet. In fact, if we compare these two pictures, then I would reckon that they're almost identical, and that the view that I'm having from this side of the magnetic of the coil is actually to suggest that this is a south pole. That part of the loop is actually behaving like the south pole of a magnet. And that's quite interesting. So if we go back to our original diagram, what you'll see, the compass needles are all pointing away. And that tells us that this is the North Pole, and sorry, this is not the North Pole. The North Pole is the red part, and this is the South Pole. And so we've got a very good picture of what's happening when we put a current through a loop. We're forming something that, while the current is passing through the loop, is very similar to a magnet, a bar magnet. And that's why we call this type of arrangement an electromagnet. It is only magnetic while the current is passing through the wire. Now, obviously, it's not a very strong electromagnet. And what we're going to need to think about is how can we increase the magnetic flux to make this a stronger electromagnet. Now, I'm sure you've done some experimenting with this, and we're going to take a look at it. But first of all, let's make sure that we understand exactly what's happening here, and you draw the pictures so that you've got a very clear understanding of the magnetic field that we observe around a loop.